Hello friends, welcome back to this video on analog communication. In this video, we are going to discuss the instantaneous sampling and natural sampling. I have already discussed what is sampling, sampling theorem, Nyquist rate, aliasing and reconstruction in my previous videos. So I recommend you to watch them first and then come to this video. So here we are discussing about the instantaneous sampling and natural sampling. Both of them are the pulse modulation technique. So first you should know what is pulse modulation. Till now we have discussed only the analog modulation, where the characteristics of a deterministic carrier signal is changed in accordance to the random message signal. So here we have the pulse as the carrier signal. So here also we are changing the characteristics of the deterministic signal of pulse in accordance to the random message signal. So which characteristics of the pulse are changed? So the characteristics of the pulses are amplitude, its on-off time and its sampling duration. So according to the different characteristics of the pulse modulation is classified into two types. The first type is pulse amplitude modulation, which is also called PAM. Now the second type would be pulse time modulation. Now the pulse time modulation is further classified into two types. The first type is pulse width modulation, and the second type would be pulse position modulation. Which are known as PWM and PPM respectively. So I have talked about them previously in my previous video, where I was discussing different types of modulation techniques as well. So I hope you remember what are exactly these three types. So now here also I'll be giving you a quick overview that what are different types of pulse modulation techniques. So here I am taking a same message signal and same pulse signal. So from here you can see the pulse is not an analog signal. So here we have different characteristics of the pulse. So first we'll see what are the different characteristics of the pulse. So first is the amplitude. So I am denoting the amplitude by A. So amplitude, you can see we have taken the amplitude to be same because it is constant. So now here we have the pulse duration, which is called T, which is also known as pulse on time. So T is pulse on time. So here we have T1. So here I will be denoting it. So this is T1 and T1 is pulse of time. So generally the T1 is greater than T. So it's a general case, you can take T1 to be equal to T as well. So now here we have TS as well. So TS is the difference between two samples. So TS sampling time. So now these are some of the characteristics of the pulse. Now these characteristics are changed in accordance to the message signal. So I'll write A also. A was amplitude. So these characteristics of the pulse will change in accordance to the message signal. So let's see what is PAM. I hope you remember. So you can see the amplitude of the pulse is changed in accordance to the message signal, and this process is called PAM. So this is PAM. Now coming to the pulse width modulation. So here the width of the pulse will change. Now TS remains same. So TS remains same, only the width change. So here if I make it, so you can see we have TS to be same, only T is changing. So this was pulse on time. The pulse on time will change. Obviously the pulse off time will also change because TS is same. So now coming to the pulse position modulation. So here we'll be having different TS. So you can see here TS is less and here TS is more. So I can say TS is changing. Now if I talk about the pulse on time, the pulse on time will remain same. T will remain same here, and both of them have the same amplitude throughout the length. So the amplitude is also constant, but here the amplitude is changing. So now if I talk about this TS, so I already know the Nyquist rate. The Nyquist rate gives the condition that Fs is greater than equal to twice of the maximum frequency. I am taking the maximum frequency to be W. So Fs is greater than equal to 2W. So if I take the reciprocal, so 1 upon Fs, now sign will be reverting. So 1 upon 2W. What is 1 upon Fs? 1 upon Fs is Ts. So I can say Ts is less than equal to 1 upon 2W, then only these types of modulation will take place. So the only condition is Ts is less than equal to 1 upon 2W, then I can modulate my pulse and I can recover my signal back also. So now coming to the topics, instantaneous sampling and natural sampling. So first I'll be talking about the instantaneous sampling. So instantaneous sampling is a process of sampling where the message signal is multiplied with the impulse train. So this is denoted by del T minus and Ts. So my message signal when multiplied with the impulse train, then I'll get the instantaneous sampling. I have already discussed this process in the sampling theorem as well. So what happened? Mt is multiplied with summation n is equal to minus infinity to infinity del of T minus and Ts. So here also we had summation. So now this is my output y of t, which is the amplitude modulated signal. So here what would happen if I take this mt inside this summation? So here yt would be equal to summation n is equal to minus infinity to infinity m of n ts multiplied with del of t minus and ts. So now this is my y of t. So now if I denote y of f would be equal to fs summation n is equal to minus infinity to infinity m of f minus and fs. So here if I talk about the circuitry to generate the instantaneous sampling, so the circuitry looks like this. So here we have x, sorry, this is my empty. I am denoting my input with the m of t. So this is my empty, this is the input. So here we have a switch and here we have the y of t. So here we have another connection. So now this switch is connected here instantaneously, then again it is connected here. So after the 0 instant of time, so the instant of time that this switch is connected to this terminal is tending to 0, and just after that this switch comes here and again this process repeats. So from here I can generate the instantaneous sampled output yt with the help of mt. So now I hope you understood how we can generate it. So now I talked about this circuit where I said this switch should be connected at the time which is tending to 0. Is it possible practically? No. So it's not possible practically. Now when these two signals are multiplied, I'll get the signal like this. So y of f was fs multiplied by the message signal at the different instant nfs. So the difference between them would be fs. So now this is the output y of f. So now from here you can see the duration of this impulse is tending to 0. So now t is tending to 0 here. You can see directly the t width is tending to 0, then only the pulse will become the impulse. So because of this it is not possible to generate practically, and because it has 0 width the noise can interfere more. So now noise interference would be very high. And lastly, because the width is again 0, is tending to 0, so now the power transmitted by this signal is 0. So because this signal is carrying almost 0 power, it can be changed very fast because of noise, and now it cannot be transmitted in the channel to a long distance. So now the power carrying capability is very less, due to which it cannot be transmitted over long distance. Now I'll be talking about the natural sampling because of all these limitations. So these are all the limitations. Don't get confused. These are limitations. So because of all these limitations, I have another type of sampling method, which is natural sampling. So what happens? First we'll be seeing the circuit. So it's a simple circuit. Here we have a switch. This is switch. So now it is connected to this terminal for some duration of time, which is denoted by t. The time duration is the width of the pulse. So according to the width of the pulse, this switch is closed. Just after that it is opened. Then again it is closed. How much late it is closed? It is closed at Ts instant of time, which is sampling time. So T and Ts will change this switch, and accordingly we'll get the output. So here we have the output, which is like this. We have pulses of finite duration, which is changed in accordance to the message signal. So here the amplitude is changing in accordance to the message signal. So now if I talk about these pulses are denoted by the Fourier series. So now I have pulse which are repeating periodically, so I can have Fourier series representation of the pulse. Now the Fourier series representation of the pulse is denoted by Pt, which is equal to summation n is equal to minus infinity to infinity Cn, it is multiplied with e raised to power j 2 pi nt upon Ts. Now I know 1 upon Ts, it is Fs. So now I can denote it as summation n is equal to minus infinity to infinity Cn e raised to power j 2 pi nt into Fs. So now this is the Fourier series representation of this pulse. So now what is Cn? So Cnt, if I talk about the time domain, in the frequency domain, these are represented by the rect function. So here in the time domain, it is represented by At upon Ts sync and Fs t. So now this is my Cnt. So now I'll be putting the value of Cn here and I'll be finding out what is my Pt. So Pt is summation n is equal to minus infinity to infinity At upon Ts sync nfst into e raised to power j 2 pi nfst. So now this is my Pt. So here how I am getting the Yt. Now Xt is multiplied with Pt and I'll get the Yt. So Yt is Xt multiplied with the pulse. So now don't get confused. Here I took the message as empty and here I am taking it as Xt, just to differentiate between the instantaneous sampling and natural sampling. So here I'll multiply both of them. So y of t would be equal to summation n is equal to minus infinity to infinity At upon Ts sync nfst e raised to power j 2 pi nfst into xt. So now here I know e raised to power j 2 pi nfst into xt. It's the frequency shift property. So here it is represented as xf minus nfs in the frequency domain. So here I can represent this function as summation. So I can take At by Ts outside. Now these were constant for the pulse. So n is equal to minus infinity to infinity sync of n fs tau, it is multiplied with x of f minus n fs. So this is my output y of t. So now from here you can see xt is graded with the help of sync function. So what kind of output here I'll be getting? So here I'll be drawing it. So here the output would be yt would be graded with the help of sync function. So here I'll be having different samples, but these are graded with the help of sync function. So this is output of natural sampling. So I hope you understood what is natural sampling, how mathematically we can derive the output in the natural sampling, what is instantaneous sampling. Mathematically, how I can derive the output, I have talked about this output in my previous video also, so I hope now you are very clear about this. So if you have still any doubt here in the mathematical part, you can again rewind the video and you can check it again. Still, if you encounter any doubt, you can put the doubt in the comment and I'll try to resolve it as soon as possible. I hope you like this video. If you like it, share it with your friends, subscribe the channel and push the like button. Thank you.